All right, so here on this last table, we're going to show you on the next, that's 2 pages here. It compares four widely used growth models. So each model, which is going to be from column 2, consists of a first order differential equation and an initial condition that specifies y of 0, the value of a solution y when x is equal to 0. Now the differential equation has a family of solutions, but there's usually just one solution that we want to look at. Now the particular solution in column 3 also satisfies the initial condition, just as there is a family like y equals x squared plus k. So depending on what k is, you're either up or down, as far as how your graph goes. So you can, if you have, where'd my thing go? You have it here or here or here, depending on k. And so that's the family of antiderivatives for g of x equals 2x, okay? But only one antiderivative, the particular antiderivative y equals x squared plus 5, also satisfies the condition that y of 0 is equal to 5. So that's where we have that offset by. Okay, now the graph of the model solution is shown in column 4, and it's followed by a short and necessarily incomplete list of areas where the model can be used because we don't want to put all of them in there. So we have unlimited growth. This is the rate of growth is proportional to the amount present. And so we have dy dt is equal to ky, and k and t both have to be greater than 0, and y of 0 is equal to some c. Our solution is going to look something like that. This is going to be our exponential kind of growth function. So this is kind of short-term population growth, people, bacteria, etc. Growth of money at continuous compound interest rate, and price supply curves. So that's what we'll see with unlimited growth. Now we have exponential decay. That's rate of decay is proportional to the amount present. And dy dt is equal to minus ky in this case, not positive. And k and t are both greater than 0, and y of 0 is equal to c. And so we get this function, and so it's decaying, looks like that. So this could be depletion of natural resources, radioactive decay, absorption of light and water, price demand curves, atmospheric pressure, where t is the altitude. And so as you go up, the pressure goes down. Then we have something called limited growth. So it's the rate of growth is proportional to the difference between the amount present and a fixed limit. And so here we have dy dt is equal to k times m minus y. K and t both greater than 0. Y of 0 equals 0. And here we get the solution that we kind of saw a little bit ago. We have m minus m times e to the minus kt. And so that's kind of goes up and we reach a plateau. We never reach that m value. We get very, very close, but we never reach it. These are sales fads, new phones, trending fashion, depreciation of equipment, company growth, learning, etc. Okay. And then the last one is something called logistic growth. And here we have the rate of growth is proportional to the amount present and to the difference between the amount present and a fixed limit. So here, instead of what we had before, we see dy dt is ky times m minus y. And so we get this m over 1 plus c. And so our function looks like this, m over 1 plus c e to the minus kmt. And we get this, it starts at some point and then it goes up. And again, it reaches kind of a max, but we have this point of inflection where it's going from concave up to concave down. And here, this is kind of long-term population growth. It really increases, but then it slows down based on, food or something else. We can't keep going higher. There's a limiting factor on where people can live. Epidemics also follow this kind of curve, sales of new products, spread of a rumor, and company growth. So there's all kinds of things that we can do here using those models. So what I want to do is kind of do some example general or particular solutions of differential equations for first order. All right, so probably take a couple pages here. So let's look at 9. So here we have dy dx equals 6x. Okay, so to do this, we're going to multiply both sides by dx. We have dy equals 6x dx. Now, what are we going to do? Well, we're going to integrate both sides. Okay, now I could have put that integral here and it would have been just fine because it can go on either side, but I'm just going to leave it like that. Well, the integral of dy is y. The integral of that's going to be 6x squared over 2 plus c, or 3x squared plus c. And so that's what my y is equal to. What about 11? All right, so here we have dy dx equals 7 over x. Again, multiply both sides by dx. So we have dy equals 7 over x dx. And again, I'm going to integrate both sides. Now here I might think about this and say, well, let's take that and do something that looks like that. And so then I can see for sure, hey, I have 1 over x. I know that when I do that, now if I take that integral again, put it here, I get y equals 7. This is giving me ln absolute value of x, and then plus, again, some c. Because these are the this is the one we don't have to figure out what c is. Some of them, we actually have to find a particular solution. These, we're finding the general solution. All right, what about 13? 13, we have dy dx equals e to the 0.02x. Again, multiply both sides, and we have e to the 0.02x dx. Now, if I take and do the integral of both sides, now I have to think about this one. Well, what do I have here? Well, this time I have to think about, oh, I don't have just e to the x, I have something else. So I'm going to have to let u equal 0.02x and du equals 0.02 dx. So that means I'm going to have to multiply this by 0.02 here to get that 0.02 here, but I'm going to have to take and divide by 0.02 out in front. So then I get y equals, because I'm just going to go ahead and take that derivative so I don't have to write it again, 1 over 0.02 integral of e to the u du. Okay. And so then I can say, okay, well, if I do that, that's going to be, well, 1 over 2, that's probably a number. So 0.02 to that equals 50. So it looks like I'm going to have 50, and then I'm going to have e to the 0.02x, and then plus c. Okay, and so that should be what I get for my thing. So y equals this whole thing. Now you could have left it 1 over 0.02, but then you have kind of a decimal in the denominator, and it's kind of like putting a fraction in a denominator. We usually don't like that, and so here we're going to go ahead and convert it to the whole number, and that's what we have. All right, so 13, so 15. So here we have dy dx equals what? X squared minus x. Now this time we have a specific thing. So we're going to have to come back and figure out what c is once we get this done. All right, so now if we multiply both sides by that, so we'll get dy equals. Now I'm going to think about this and say, okay, well, we're doing an integrate. So let's say that's x squared dx minus x dx. So I know it's going to end up being this whole thing times dx, and then I can split that into two integrals, and then I have a dx on both of them, so that makes it easier. So now I have y equals, that's going to be x cubed over 3 minus x squared over 2 plus c. Now, x and y are both 0. Well, if that's 0 equals 0 over 3 minus 0 over 2 plus c, that means c is equal to 0. So my actual equation is y equals x cubed over 3 minus x squared over 2. And then that would be my final solution. All right. Maybe we have enough room for 17, but we won't for sure have 19, I don't think. So 17 is dy dx equals a minus 2x e to the minus x squared. And again, this time we have 0, 3. So multiplying both sides by dx, we get dy equals a minus 2x e to the minus x squared dx. All right, so let's let u equal, and we'll let that equal this, a minus x squared. So du equals what? A minus 2x dx. So now I can say, okay, well, now I'm going to have an integral of dy equals, and now 2x dx, so well, that's this piece and this piece, so that's good. And then that's going to be basically just the integral of e to the u du. So that's just going to be y equals e to the u plus c. And so that's y equals e to the negative x squared plus c. But we said that x is 0, y is 3. Well, if this is 0, we get 3 equals 1 plus c. Subtract 1, c equals 2. So my actual equation is y equals e to the minus x squared plus 2. And that would be my actual equation that's specific for going through the point 0, 3. All right, so now let's turn the page and we'll do that last one here. And so we're going to have 19 is dy dx equals 2 over 1 plus x. Okay. And then we also had it, let's write down, I think it was 0, 5, right? Yeah, 0, 5. So we have 0, 5. Okay, now we have everything. All right, multiply again both sides by dx. We have dy equals 2 over 1 plus x dx. So now if I look at that as the integral, that's the integral of dy equals 2 times the integral of 1 over 1 plus x dx. Well, this is one of those that I think I'm just going to say, well, let's let u equal 1 over 1 plus x, du equals, oh, not 1 over 1 plus x, sorry, just 1 over 1 plus x. And then du is equal to 1 dx. And so 1 dx, 1 plus x. So then we have integral of dy equals 2 times integral of 1 over u du. Okay. Now, given that, what do we have? Well, that's going to give me y equals 2 ln absolute value of u and then plus c. Well, u is 1 plus x plus c, and then that's y. And now we plug in this, so 5 equals 2 ln, absolute value of 1 plus 0 is just 1, and then plus c. Well, ln of 1 is going to be 0 times 2 is 0, so c equals 5. So we get y equals 2 ln 1 plus x, and then plus 5. And these are absolute values still. Okay. But this case, we're going to be up by 5 is what we've done. We've translated it up 5. Okay. All right. So that's all I have for this section on the differential equations. Hopefully that helps.